first example, I got this out of the exercise set at the end of section 9.1. At California, what I would recommend that you do on these is pause the video when you see the example come up, write down whatever you need to, copy it down, or write down where it is in your book. You can either try to work it without me first, or then you could turn it back on and watch me work through the problem. And then when you're done, you can see whether you're right or wrong. So the average teacher salaries in California, the yearly average is the $64,000, and in New York they were at 62 something. We took random samples of 45 teachers from each state to get the two sample means given there and the population standard deviations that were both given there. Okay. Now understand that up at the beginning they said assume these populations are normally distributed, so we're okay to proceed through in the problem. I'm only worried about an alpha being 0.10 here, and I want to know if there's a difference in the means of these salaries. So many of the problems in chapter 9 are just saying, is it this or is it something else? And so we're going to have a bunch of two-tailed tests. But there are some that are only one-tailed. So we'll try, I don't remember how many of those I had in the examples because I didn't have much to choose from. But if I want to see and test whether or not there's a difference in the salaries, my null hypothesis is always going to be that the two means are equal, and difference means I have a two-tailed test of not equal. If alpha is equal to 0.10, and I have a two-tailed test, my z sub alpha over 2 scores are plus and minus 1.65. From here, if I want to compute my test statistic, we're going to take the difference of the means, 64,510 minus 62,900, okay, minus, if we're testing an equal to, not equal to case, that means if we subtract mu1 minus mu2, if they're equal up in the top, this is going to be a 0. Okay, occasionally there's a handful of problems where that's not 0 scattered throughout the exercises, but they're few and far between. Okay, if we're testing to see whether the means are the same or if they're different, that means the difference of them would be 0 if they're the same. Since we're dealing with population standard deviations, those two guys were 8,200 and 7,800. Okay, those are squared. This is from the formula in the last video. It's also on your note card, which I can't show you. I could only show you what's on my computer screen. I can't put the overhead on these videos. Okay, both sample sizes were 45. Okay, the sample sizes don't have to be the same. In some of the problems they are, some of them they're not. Okay, if and your calculator can hold all of this if you ask it to do this in the right way. So many of you will want to break it into smaller pieces. If you do the top and the bottom separately, the top number is 1610. If you find the square root of all that mess on the bottom, you get 1687.075. I took it out to several places. So when you divide that on my scribbled notes here, you get 0.95. The 0.95, we come back up here and figure out where it lies. Okay, these blue shaded tails in my two-tailed test, that's where I would reject the null hypothesis. 0.95 is to the left of 1.65, which means I'm not going to reject the null hypothesis. So in words, I would say do not reject the null. There is not enough evidence to support the claim that that the mean salaries are different. We're not going to reject the null as I write from big to small. There's not enough evidence to support the claim that the mean salaries of those two states are different. I was not in the rejection region, so I cannot reject the null. Not at this level of significance. Okay. This problem is problem 7 from your textbook. Again, pause the video so you can get things written down. And when you're done, start it back up, because we're going to jump right in and get started. Here we're talking about commuting times of two different populations. We've got Miami and Baltimore. And always, my null hypothesis is that those two means are equal to each other. It says, can I draw the conclusion that they're actually different after I've taken this sample and I've done my work? You notice my sample sizes are 40, so even if they didn't tell me I was normally distributed for my population, by the time the sample sizes go above 30, I know that I'm okay there. Also, notice that I put in bold in both problems that this says population standard deviation. That's how I know I'm using z-scores here, and not the student's t-distribution, which we'll do in one of the next videos. So again, I have a two-tailed test, and my alpha here, that's supposed to say the 0.05 level of significance. And so a two-tailed test for my alpha being, sorry, I can't write one thing and say another, being 0.05 or plus and minus 1.96. All right, so we find our test statistic. On top, that'll be the difference of the two means. There's no rule that says you have to call one of them specifically mu1 and one of them specifically mu2. I just use the left one as the first sample and population and the right one as my second. Again, we're testing to see whether they're the same or different, so the difference in the two would be 0. On the bottom, my two standard deviations that I was given are 7.2 and 9.1. Remember that those guys are squared. And it's over the sample size, which again in this case, both of them are 40. Some of the samples, or some of the examples that we'll do, there's different sample sizes between the two populations. On the top, when we subtract, we get negative 6.7. On the bottom, when we figure out that radical, it's 1.8347, if I can read my handwriting. But even if that's not exactly right, I know that the quotient, that part I can read, is negative 3.65. I take my negative 3.65, I come up to the table here, and I notice it's to the left of negative 1.96. If I'm in either of those blue shaded regions, that's where I determine that I'm going to reject the null hypothesis. I need to extend my page, sorry. So I'm going to say that I need to reject the null hypothesis here. Okay, what I have figured out is there's enough evidence to support the claim that the commuting times are different between the two communities. There we go. Something else that we can do along with hypothesis testing is they reintroduce the idea of confidence intervals here. And so I'm going to ask on the next slide, I want to determine a 95% confidence interval for the true difference of the means. The formula for the confidence intervals are found in your book. They're also on your note card, I'm sure. If we look there under chapter 9, and they're kind of a mess. But we actually already found what we needed. Maybe I can dual page this guy. For the confidence interval of the difference in those two means, okay, what we'll have on the left end, I did not leave enough room, the difference in the x bars, okay, minus the z-score, z sub alpha over 2, which will always be the two-tailed z-score, times the square root of, I'm going to put star here, okay, where star, because I don't have room, is this stuff. And then at the top end, it's going to be the same value plus the z-score times the square root of star, star again being that stuff in the circle, the sigma 1 squared over n1 plus sigma 2 squared over n2. And since we already did the hypothesis test on this, same with my 9.2 example, then that saves us a little bit of work. I know the difference in those two samples there is negative 6.7. For a two-tailed test, I know that my z-score is 1.96, and I found out the square root of that stuff was 1.8347. Had I not done the hypothesis test, then I would have to go through and do the arithmetic and find all those things. The low end of that confidence interval is negative 10.3. And the high end is negative 3.1. Now, because we're talking about the difference of two means here, it's okay to have negative numbers there. Okay, before when we said what's the confidence interval that for the mean number of credit hours a student is taking, or the mean test score on the ACT, or the mean number of hours of sleep a student gets the night before a calculus exam. Okay, and those could not be negative values. But here, since we're subtracting the two means, what that tells us is that the Baltimore mean is bigger than the Miami mean. When we subtract them, I get a negative number. So we're just saying it's bigger by 10.3 at most and 3.1 at the least.